Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 9, hello. Scaling principle for volumes. Classwork opening exercise A. For each pair of similar figures, write the ratio of side lengths A to B or C to D that compares one pair of corresponding sides. Then complete the third column by writing the ratio that compares the areas of the similar figures. Simplify ratios when possible. Okay, so they want us to reduce. All right, so here's what they've done. They said that triangle A is similar to triangle B. A is to B. And side 6, side 6, length 6, is to length 4. And that's what we're doing. We're just doing a ratio setup. So the altitude or height, 6 to 4, and the base is 3 to 2. And then what you do is take the ratio of the areas. So area is 1/2 base times height. 6 times 3 is 18. Half of 18 is 9. 4 times 2 is 8. Half of 8 is 4. So it's 9 to 4. But that's also 3 squared to 2 squared. Okay, so, All right, so let's move on and see what happens down here. So I have rectangle A is similar to rectangle B, and I have a length of 3 to a length of 15. I also have a width of 1 to a width of 5. So area is base times height. So 1 times 3 is 3. And 5 times 15 is 25, 5, 75. So how did we get that? Okay, well, we can't see anything here. So 1 squared is 1, 3 squared is 9, so that's not happening. Oh, wait a minute. Simplify ratios when possible. So this can be reduced. 7 plus 5 is 12. 3 will go into 12, so 3 goes into 75. So I can reduce this. 3 goes into 3 once. 3 goes into 7 2 times with a remainder of 1. 3 goes into 15 5 times. So now I have a ratio of 1 to 25, and that would be 1 squared to 5 squared. So it's the shorter side to the shorter side squared. Okay, continuing on. 6 to 4, 3 to 15. What can we do here? Altitude to altitude would be 4 to 2. Altitude 10 to 5. Those all reduce. We can reduce those down to 2 to 1. Okay, 2 to 1. 5 goes into 10 twice, 5 goes into 5 once, 2 goes into 4 twice, 2 goes into 2 once, so I can reduce it down to 2 to 1. Okay, so now I find the area. Well, it's the base 10 times 4, which is 40, and take half of that, so it's 20. And the area of this is 5 times 2, which is 10, divided by 2, which is 5. Reduce this. 5 goes into 20 4 times. 5 goes into 5 once. And 4 is 2 squared, and 1 is 1 squared. And that is our ratio, reduced scale factor, 2 to 1 squared. Okay, page 2 brings us some more of the same. And we are dealing with 2 triangles that are similar. Triangle A is similar to triangle B. And our altitudes ratio would be 4 to 12. So I write 4 to 12 for my altitude. My base is 6 to 18. 6 goes into 6 once. 6 goes into 18 3 times. 4 goes into 4 once. 4 goes into 12 3 times. So our ratio reduced is 1 to 3. Now when I find the area, 6 times 4 is 24. Half of 24 is 12. and 12 times 18, well, 18 times 10 is 180, plus 2 more, which would be 36, would be 216. Half of 216 is 108. So 12 goes into 12 one time, and 12 times 9 is 108. 1 is 1 squared, and 9 is 3 squared. Okay, so you see a pattern of starting to appear here. Now we have a rectangle A similar to rectangle B. Let's do the base or the length first. 5 is to 10, as our width is to width, which is 1 is to 2. Okay. This is a misprint, by the way. That's C and that's D. All right, so our ratio is 1 to 2. So now if I find the area, area is base times height, or length times width. 5 times 1 is 5, and 10 times 2 is 20. 5 goes into 5 once, 5 goes into 24 times. 1 is 1 squared, and 4 is 2 squared. So as you can see, again, our ratio of our shorter side reduced all the way down squared is the ratios of our areas. B, state the relationship between the ratio of side A to B and the ratio of the areas of A to area B. Okay, so when the ratio of the side lengths is A to B, then the ratio of the areas is A squared to B squared. 2, make a conjecture as to how the ratio of side A to B will be related to the ratio of the volumes, volume S to volume T, and explain. Okay, so I would say when the ratio of side length is S to T, then the ratio of the volumes will probably be S cubed to T cubed. The area is two-dimensional, and the comparison of areas was raised to the second power. Since volume is three-dimensional, I think the comparison of volumes will be raised to the third power. What does it mean for two solids in three-dimensional space to be similar? Okay, it means that a sequence of basic rigid motions in dilations maps one figure onto the other. Okay, page 3 brings us to exercise 1. Each pair of solids shown below is similar. Now we're talking about solids. Write the ratio of side lengths A to B, comparing one pair of corresponding sides. Then complete the third column by writing the ratio that compares the volumes of the similar figures. Simplify ratios when possible. Okay, so I'm going to take the height to height, which is 10 to 8. The radius of the circular base is 5. The radius of this circular base is 4. 10 over 8 divided by 2, or 10 to 8 divided by 2 is 5 to 4. So there is our reduced ratio. So what we're trying to see, what we were saying in the prior page is we're thinking that we're going to get ST becomes S cubed T cubed, and that's what we're trying to see. So keep that in mind. What's 5 cubed? Well, it's 125, and 4 cubed is 4 times 4, which is 16, times 4 is 64. So we're looking for 125 to 64 if what we said is true. So now we're going to find the volume of each cone. So right here, I'm going to do volume of a cone is the base area times the height divided by 3. And our base area in this case is a circle, and the area of a circle is pi r squared times the height over 3. So the volume is going to equal pi. The radius of this is 5, so it's going to be 5 squared times the height, which is 10 all over 3. So therefore we get the volume to be 25 times 10, which is 250 pi over 3. So I'll write this here, 250 pi over 3 is 2. So now we have to do the same for the next one. I'll erase this. And now we're going to do this one. And volume equals base area times height divided by 3. The volume of a cone is the base area, which is pi r squared, times the height divided by 3. Write this every time, and you will remember the formula. So then we substitute in our givens. Pi, the radius is 4 squared and the height is 8 divided by 3. So the volume is 4 squared, which is 16, times 8. Okay, 16 times 10 is 160, minus 32 is 128. So I get 128 pi divided by 3. So this is going to be 128 pi divided by 3. Okay, these reduce. The pi over 3's cancel. The pi over 3's cancel. We get 250 to 128. Remember what we were saying over here. We're trying to see if we're going to get 5 cubed is to 4 cubed. So I'm just going to work backwards here now. 5 times 5 is 25 times 5 is 125. Where does 125 come from this? Well, it's half of 250. So we're going to divide this by 2. So we're going to divide this by 2. 64. Well, 4 times 4 is 16. 16 times 4 is 64. So we do get our 5 cubed to 4 cubed. So this is true. So what we suggested, what we said we thought, right here, see the word probably, we are confirming. So let's continue and see if it's true for other shapes. Now let's do this rectangle. So the ratio of the base is 3. The ratio of this base is 15. The ratio of the, well, that's length. The ratio of the width is 1. The ratio of this width is 5. And the height is 2 to 10. Well, this is our reduced piece, okay? It's a third of this one and it's half of this one. So we're looking at 1 to 5. So I'm going to, down here, I'm going to put 1 cubed is to 5 cubed, and 1 cubed is 1, and 5 cubed is 125. So this is what we're trying to get. And the area equals length times width times height. So the area of the little one is length times width times height. So the area is 3 times 1, which is 3, times 2 is 6. So I get 6. And then the area of the other one is L times W times H again. And the area is 15 times 5 times 10. So the area of this one is 5 times 5 is 25. 15 times 5 is 75. Times 10 is 750. So 6 is to 750. Well, I need to get down to 1, so I'm going to divide these by 6. 6 divided by 6 is 1. 6 goes into 7 once. 6 goes into 15 2 times with a remainder of 3. 6 goes into 35 times. And as you can see, that's what we got. And we take the cube root and we get this. So you cube the ratio of its sides and you get the ratio of its area cubed. The sides cubed is the ratio of the area, is what I probably should have said. All right, so we're going to do this again. So here we have a triangular prism with a base of 6. And this base is 18. This height is 4. This height is 12. And the length of each is 12 to 36. Well, we can reduce these down. This is the easiest one to reduce. 4 goes into 4 once, 4 goes into 12 3 times. And 12 times 3 is 36, 6 times 3 is 18. So here is our ratio. So we're looking for a 1 cubed is to 3 cubed if this, oops, not cubed, squared. No, it's cubed. That's right. 1 cubed is 1, 3 cubed is 27. So that's what we're looking for. So now we're going to find the area of these triangular prisms. Well, the area of the triangular prism is the base area times the height. The base area in this case is a triangle. The area of a triangle is 1/2 little b times h times the other height. Okay, so don't confuse the two h's. They're not the same. So let's make this one a capital, I guess. So area equals 1/2. The base of this triangle was 6. The height was 4. And the length of the pyramid or the triangular prism was 12. All right, let's get rid of this half and get rid of this 12 and make it 6. I like getting rid of the largest even number to make it easier to multiply. And 6 times 4 is 24. 24 times 6, 6 times 4 is 24. Carry the 2, 6 times 2 is 12, plus 2 is 144. So the area of this one is 144, so I'll put that here. And now we do it again for the other triangle, this one. So the area equals capital B times H, and I'll use a capital H in this case because the base area is 1/2 little b times height and then times the big height. So the area is 1/2 18, 12, and 36. Running out of room here. All right, so I'm going to get rid of my largest half, which is 36. So it's 18 times 12 times 18, a little bit large for me to try to do in my head. 18 times 18 times 12 is 3,888. So since we are getting to 1 here, then I would divide, it'd be 144 times. So if I take 3,888 and divide it by 144, I should get 27. And sure enough. So it's 1 to 27, which is 1 cubed to 3 cubed. So what we said in the prior page has turned out to be true. 5 to 4, 5 cubed to 4 cubed. 1 to 5, 1 cubed to 5 cubed. 1 to 3, 1 cubed to 3 cubed. Okay, a couple more examples from on page 4 here. So let's continue with this. And this should just be really quick now. So let's set up our ratios. The height of our base is 3. The height of this base is 2. The base of the base is 6. The base of this base is 4. The height of the prism is 6. The height of this prism is 4. So the reduced ratio is 3 to 2. So area of a triangular prism is capital B times H, the base area. So the base area is a triangle. So that's 1/2 little b times height. And let's make that a capital H again, times height capital. So the area equals 1/2. The base of the base is 6. The height is 3 of the triangle, and the height of the prism is 6. All right, so I can get rid of my 6 here and make it 3. So the area is 3 times 3, which is 9, and 9 times 6 is 54. So the area is 54 units, or volume, I mean. The volume is 54 cubic units. And so then I'm going to do it again for the other one. A equals capital B times H. A equals 1/2 little b times little h times big H. A equals 1/2. This little b is the base of the base, 4. This lowercase h is the height of the triangle's base, which is 2. And the height, capital H, is the height of the prism, 4. So this half will make this 4 a 2. So my area is going to be 2 times 2, which is 4 times 4, 16. So I get 54 to 16. Okay, 2 times 2 is 4 times 2 is 8. So I want an 8 here. So I took that half of that. Well, half of 54 is 27. Half of 54 is 27, so we have a 27 to 8 ratio. And the cube root of 27 is 3. So 3 cubed is 27, and 2 cubed is 8. And sure enough, there you go. All right, one more. All right, length 4, length 4D, width 2, width 20, height 3, height 30. Okay, so these all reduce. If I reduce the smallest one, it will end up being 1 to 10. So this is our ratio reduced. So let me erase all this now. So the area of a rectangular prism is length times width times height. So the area of the little one is 4 times 2 times 3. So the area of the little one is 4 times 2, which is 8 times 3, which is 24. So it's a 24, 2, and the area is length times width times height again. So the area equals 40 times 20 times 30. 40 times 20 times 30. Okay, 4 times 2 is 8. 8 times 3 is 24. And we have 3 zeros. Okay, so it's 24 to 24,000. So to get down to 1 to 10, we need to divide by 24. So 24 divided by 24 is 1. And 24,000 divided by 24 is 1,000. So my ratio is 1 to 1,000. Well, 1 cubed is 1. And 10 to the third power, 10 cubed is 10 times 10, which is 100 times another 10 is 1,000. So our ratio went to 10. 1 to 10 became 1 cubed to 10 cubed. All right, number 2. Use the triangular prism shown below to answer the question that follow. Calculate the volume of the triangular prism. Volume equals base area times height. And let's use a capital H again. Volume equals the base area, which is a triangle. Area of a triangle is 1/2 base of the triangle times the height of the triangle times the height of the prism. So volume equals 1/2. The base is 3. The height is also 3. And the height of the prism is 5. Don't confuse the two heights. Okay, I don't have any even numbers, so I can't get rid of my half. So volume equals 1/2, and 3 times 3 is 9. 9 times 5 is 45. Half of 45 is 22.5 units cubed. So the answer is 22.5 cubic units. Okay, B says, if one side of the triangular base is scaled by a factor of 2, the other side of the triangular base is scaled by a factor of 4, and the height of the prism is scaled by a factor of 3, what are the dimensions of the scaled triangular prism? Okay. If one of the side of the triangular base is scaled by a factor of 2, so I'm going to multiply this by 2. The other side of the triangular base is scaled by a factor of 4, and this is the other triangular base, so I'm going to multiply it by 4. And the height of the prism is scaled by a factor of 3. That's all they're doing here is they're asking us what the new dimensions of the scaled triangular prism would be, and it would be 2 times 3, which is 6. And 3 times 4, which is 12, and 3 times 5, which is 15. So we have a 6 to 12 to 15. Actually, I'm setting up a ratio, and that's not right. It'd be a 6 by 12 by 15 triangle. And it would not be similar. All right, page 5 says to calculate the volume of the scaled triangular prism. Let me go back and get the values. I forgot them. 6 by 12 by 15. All right, so let's rewrite that here. 6 by 12 by 15. So they want us to calculate the volume of the triangular prism. So volume equals base area times height. I did not say Siri, stop it. The volume of the base is a triangle, so it's 1/2 the base times the height times the capital height, and the volume is 1/2 these values. Base is 6, height 12, height of prism 15. Let's get rid of the largest even by making that a 6. So the volume is 36 times 15, 540 units cubed. Okay, so now it says make a conjecture about the relationship between the volume of the original triangular prism and the scaled triangular prism. So let's go back in that first. Let's look at the volume of the original. The volume was 22.5 cubic units. So let's bring that down and say the volume of the first triangle is 22.5 units cubed. And my new one is 540. So it says make a conjecture about the relationship between the volume of the original and the scaled triangular prism. So we scaled it up by a ratio. We scaled it up by 2 to 3 to 4. So I'm thinking that if I take that 2 to 3 to 4 that we scaled it up and multiply it by the original volume, we would get this. So let's check. So if I take 2 times 3 times 4 times our original volume, which was 22.5, I get 540. Okay, so there's the relationship. If we know the 3 sides that we scaled it up by, or the 3 ratios, this 2, this 4, and this 3, rather than finding the volume again, we can just say, well, 3 times 2 is 6, 6 times 4 is 24. So if I multiply this by 24, I'll get the volume of the new scale, which is 540. Okay, so E says, do the volumes of the figures have the same relationship as was shown in figures in exercise 1? Explain. Okay, so let's take a look. Okay, so the answer to that is no, the figure was scaled differently in each perpendicular direction. So the volumes are related by the product of the scale factors, 2 times 3 times 4, which equals 24. Alrighty, and number 3, use the rectangular prism shown to answer the questions that follow. Calculate the volume of this rectangular prism. All right, so here we go. So you say V equals capital B times H, and V equals the base area, which is a rectangle, which is length times width times the height. All right, so the B is this length times width. Yes, that's the base area, and this should have a so you can see the base. All right, but this would be the base as well. It is a rectangle, which is length times width. So the volume of this is length times width times height. So the volume is 8 times 12, or 96 units cubed. Okay, page 6 brings us to part B. And I brought the diagram over from part A because we're going to need that for this. And it says, if one side of the rectangular base is scaled by a factor of 1/2, so I'm going to scale this 8 by 1/2, and the other side of the rectangular base is scaled by a factor of 24, that'd be this one, and the height of the prism is scaled by a factor of 1/3, that'd be this one. What are the dimensions of the scaled rectangular prism? Well, 8 times 1/2 is 4 by 1 times 24 is 24 by 1/3 of 12 is 4. So the dimensions of the scaled rectangular prism would then be a 4 by 24 by 4. Calculate the volume of the scaled rectangular prism. Well, volume equals length times width times height. So the volume is 4 times 24 times 4. So the volume is 4 times 24 times 4, enter, 384. So 384 units cubed. D says to make a conjecture about the relationship between the volume of the original rectangular prism and the scaled rectangular prism. Okay, so the volume of the scaled figure is equal to the volume of the original figure multiplied by the product of the scaled factors. For this specific problem, 384 is equal to 1/2 times 1/3 times 24 times 96. And that gives us 384. Number 4. A manufacturing company needs boxes to ship their newest widgets, which measures 12 by 4 by 5 cubic inches. So I'm going to label this up because there's a lot of information in this. So the widget is a 2 by 4 by 5 cubic inches. So I'm going to calculate that and just write it up here. 2 times 4 is 8. Times 5 is 40. So this is 40 cubic inches is the space that the widget takes up. Standard size box is a 5 cubic inch. Okay, so I'm going to underline that. 5 inches cubed. Well, 5 inches cubed is 5 times 5 times 5, and that is 125 inches cubed. So the 5-inch cubes, 5 by 5 by 5, are 125 cubic inches. Okay, so those standard size boxes are inexpensive but require foam packing so the widget is not damaged in transit. Foam packing is another expense. The foam packing is going to cost 3 cents. So the foam packing costs 3 cents per cubic inch. Specially designed box are more expensive. Specially designed boxes are more expensive, but do not require foam packing, okay? Do not require foam packing. If the standard size box costs 80 cents each, so that's this standard box that we have to use packing with, then our other option is a specially designed box, costs $3 each. And the specially designed box does not require foam packing. Okay, so we need to calculate some values here. Let's switch back to my pen. All right, so what do we need to do? Well, we have to determine the area inside the box after we put a widget in it. And the box is 125 cubic inches. So if I take that 125 inches cubed and I subtract 40 inches cubed, okay, so what am I doing? I'm taking a box that's 125 cubic inches, subtracting the space a widget takes up, and that will leave me with a 5 here, and 12 minus 4 is 8. So 85 cubic inches are left over, and we need to fill that with the foam, which are 3 cents per cubic inch. Okay, so if I have 85 cubic inches, and it's going to cost me 3 cents per cubic inch, then I'm going to take that 85 inches cubed and multiply it by 3 cents. So 0.03, and it's per cubic inch. So multiply this, I get 5 times 3 is 15, 8 times 3 is 24, plus 1 is 25, and there's 2 decimal places. So it will cost $2.55 for the foam. This is foam. 3 cents per cubic inch, 85 cubic inches, $2.55 of foam. The box is 80 cents, so then I need to add 80 cents to the box, and I get $3.35. That is foam plus box. The specially designed box is only $3. So it's 35 cents cheaper than the foam and the regular box. So which box should the company choose? Well, if they want to save money, they should choose the specially designed box. Okay, page 7 brings us to the end of lesson 9. Go do your problem set.